This is ridiculous to me. The fact that this hasn't already been considered in the theory, even though we've known about it, but so this could be an incredible revolution in cosmology. The dark energy model of the universe, which won the Nobel Prize in 2011, might be completely wrong. The accelerating expansion instead is simply because time runs faster in the voids between galaxies. So first of all, I would like you to understand where our place in it is. So we exist in our local void, which, give me one that actually tells me where it is. I don't know what's the map of space is. We exist in a void. We're here. Now, if you have watched Interstellar or any sci-fi show, or actually, taken a physics class, you will understand that the closer you are to a source of higher gravity, clusters of galaxies, for example, superclusters, much more dense gravitational areas of space in comparison to voids, especially like the one that we are in, time will move slower in these areas. So we've been looking out into space and, for example, looking at 12 billion light years away. Depending on which direction we're pointing this telescope to look to find this 12 billion light years away, we have not considered the time dilation effect in these voids. So generally, we don't need to, for the most part. And we can understand this by the, understanding lambda cold dark matter theory, which came about after Einstein, who basically, okay, so in his time, scientists thought the universe was static, neither expanding nor contracting. Within general relativity, however, it should be collapsing under the force of gravity, and Einstein added this lambda parameter to balance the force of gravity and yield a static universe. Later, this was found to not quite make sense in the context that it was in. Einstein actually called this his greatest blunder. In 1929, Edwin Hubble made an incredible discovery. The further away a galaxy was, the faster it appeared to be moving away from this. He was able to determine this by measuring Cepheid variable stars, which have a consistent relationship between their brightness and their pulsation period, so they can act as distance monitors. Using these markers, Hubble found that the more distant a galaxy was, the more redshift in its spectrum of light became, meaning it was moving away from us at a higher velocity. You can just see the images of that. Now, the fact that the universe was expanding is why Einstein called this lambda addition to general relativity his greatest blunder. But then the dark energy theory came out, and suddenly this made sense again. If you run this expanding universe backwards in time, it seems like everything is expanding from a single origin point. In the 1960s, astronomers detected faint radio signals coming from all directions of space, which we assume is the Big Bang. Now, we have several models of the universe. I'm not going to go into like redshift and all of that because I'm not a physicist, but the general ideas that we have of our current possibilities of how our universe could work are either something like this, as in a crunch, something like this, which would be a continuous expansion. Or sorry, this would actually be heat death, I believe. This is continuous expansion. This would result in what is now being theorized as a big rip, but we don't actually know. The redder something is, the further away it is, or if the galaxy is just very red. So no, it's not actually whether it's red. Redshift is a spectrum of like, it is red light, but it's a lack of the other spectrums of light, and it's shifting from those spectrums to red. That means it's moving further away. Now, here's the interesting part, right? Space is extremely inhomogeneous in regions of dense galactic clusters, but space overall is actually quite homogeneous, which is why this hasn't been considered. There's not that many voids in relation to matter, right? And so most of the universe seems to be pretty much going in the same direction. They're homogeneous. There's clusters of galaxies that come together. Gravity pulls them together. And then there will be clusters of voids that are generally outside of these galaxy clusters on the outer edges, not really in the inner edges. I don't know how that works, but it doesn't necessarily matter, right? We assumed that these didn't matter because we assumed generally space is homogeneous, and so we don't have to account for the time dilation effects in these. Mass curves space-time to produce gravity, but there's no difference between being accelerated by gravity or being accelerated by a rocket. This is called Einstein's equivalence principle, and applying it to an homogeneous cosmology may actually eliminate the idea of dark energy altogether. Now, dark energy, if you remember, we discussed this when we were talking about the Euclid telescope. The Euclid telescope being the one that we sent out to map a third of the night sky in the next 6 years to figure out, A, what is dark energy? Has it been in existence since the beginning of the universe? Has the universe been accelerating at the same rate? Or has it been accelerating its acceleration? Has its acceleration been slowing down? We need to understand these concepts, and we've been looking at dark energy as the equivalence of dark matter, matter and energy, dark matter, dark energy. And we know that dark matter is real. Dark matter is the things that hold these galactic clusters together. It's the glue that holds gravity in place. But dark energy might not be a thing. We know that the lifespan of a black hole is 12 billion years and nothing but a... How could we know that if we think the universe is 15 billion years old? And also, now according to this, the universe might be more than 15 billion years old, depending on, or less, depending on where you're looking from. Remember, we're in a void, so that means time moves faster for us than it does, for example, in the Centaurus supercluster. So we think the universe is 15 billion years old. Maybe 15 billion years of time has passed for us, but only 4 billion years of time has passed for them. Not necessarily, but could happen. So in explanation of the equivalence principle, first of all, it's like, get that down. So this compartment is at rest in the Earth's gravitational field. The apple hits the floor of the compartment because of the Earth's gravity accelerating the apple downward. Well, as an atheist, it's right down my alley. I mean, me too, exactly. So, and when we're talking about acceleration that isn't based on gravity, in this environment, in a gravity-free environment, the apple hits the floor because the compartment accelerates upward, as in you are in a car and you are accelerating. That is no different in equivalence to you being accelerated by gravity. Now, this is because the further down a gravitational well you are, the slower clocks run compared to clocks further up. You can reason this yourself by bouncing a photon between two mirrors. Well, you could if you had access to technology that could do that, I suppose. The important thing here is that in the voids between large galaxies, time runs much faster than inside the galaxies. These voids are inhomogeneous. Now, if you had an initial expansion of the universe from the Big Bang, more time has elapsed in the void, possibly billions of years more. That's relative. They aren't traveling significantly closer to the speed of light than us. Well, we're all traveling at about the same speeds through space. The universe is expanding at a pretty consistent rate. We know, Vismus, I love it. We know that at the moment, it's either getting slightly faster or slightly slowing down, but there hasn't been much drastic change in how galaxies move throughout the universe, how we move in relation to them as well. We're all moving at about the same speed. The thing here being is when we're looking out into space, we are looking out through a void, through, I suppose, what was the Virgo supercluster? Give me that one. At least I can, and then find myself on this map. It's not even on here. Hydra supercluster. Saw Hydra here. So, there we go. Okay, so we are in the Canis Major void, which is what I thought. We're here. Time moves faster for us here than it does here. So if we're here and we say the universe is 15 billion years old, over here it might actually just be 5 billion years old. Now, the research behind the timescape model, as it's known, used a familiar type 1a supernova as standard candles and compared a goodness of fit Bayesian statistics. I don't know what that means. Let's look it up. We're learning together, guys. I don't know physics either. What is the Bayesian equivalent? Well, I have two data sets, one from a physical observation, temperatures, and one from an ensemble of numerical models, blah, blah, blah. I would suggest the book. Okay, I'm not going to understand this one. We can skip this. That's fine. Now, you can do a lot of statistical trickery to get your favorite results. Obviously, we all know this. But why should this be taken seriously? The universe is emphatically not homogeneous. We do know this. There are void regions and there are thick clusters. Void regions do have faster clock rates. We know this as well, based on how time moves in relation to gravity. Galactic superclusters and filaments, and this should be accounted for in any model of expansion. So dark energy is supposed to make up 2/3 of the universe's energy content. Yet it doesn't correspond to anything we observed experimentally, which doesn't matter. That doesn't mean it's not real. It solely exists to explain this anomaly of distant supernova redshift. That's what matters, is it's almost exactly the same idea of Einstein of, well, this doesn't make sense. Let me add something that makes it make sense. How fast is this difference? It depends on how much gravity you have. Again, so this void, the Copernicus or the Boots void would have less gravity than even our void, the Canis Major void. We have more mass in this void than they do. They have much more space and less mass, faster time dilation, as in from the Boots void, if you are, I don't know, in this galaxy, that tiny little 1 pixel galaxy right above my cursor, time might have moved 30 billion years. That's how much you might be looking back and seeing how old the universe is. And it's just, this is common sense if you think about it. We've known for a Feliz Navidad, for a long time that gravity does influence time. The fact that it hadn't been accounted for, because generally the universe is considered to be homogeneous, is ridiculous. Because there are inhomogeneous bits of space. And if we're trying to figure out how long ago the universe was, I don't know, came into existence, or how far away something is, it matters which direction that we're pointing our telescope through, and whether it's moving through a void or moving through galactic clusters, and the amount of mass in these clusters will also dilate the time. Now, dark matter is real, but dark energy might not be. Dark energy might just be what we use to explain the time dilation effect. You can't divide by 0. I'm aware of this. I thought time moved faster in higher gravity. No, much slower. If you, like in Interstellar, if you land on a planet that is closer, like that's close to a black hole, time will move very quickly for you, but very, very slowly for everyone observing you. So from the observer's perspective, it's based on your perception. That's what I'm trying to say. And again, we are in the Canis Major void. We think the universe is 15 billion years old. A civilization in the Boots void might be thinking it's 50 billion years old. In the realm of cosmology, the inquiry into whether space has an endpoint is fundamentally intriguing. However, whether the universe ultimately concludes, well, actually coming to that is the end of this. These are the two models that we've been using. This was the one that had been the mainstream, the contemporary idea of the heat death of the universe. But now, based on our new understanding of adding in these time dilation theories, that might not just happen. We might go for whatever ends up as a big rip. The end of the universe is a stupid thing to try and think of. That's not my concern here. My concern here is now knowing time dilation is effect, we can use that in looking at other bits of news in regards to space. The most comforting universe death for me would be one that is part of a cycle. I mean, we'd all be dead anyway. You know, technically, since relativity is a thing, trains are time machines. I suppose, depending on, you know, the context in which the train is being used, yes. Again, if there's more mass on this train, like if you could somehow get a small little ball, like a bouncy ball with the mass of, I don't know, the sun on this train, then yeah, it makes a difference. Merry Christmas, everybody. How do I know that the Fruityverse exists? Well, after several alcoholic beverages last night, I went there. True. I thought we knew how old the universe is. Well, again, we know how old the universe is based off of our relative understanding of time. If you look at how old the universe is from a different cluster, or even in like a supercluster of planets, that's a different answer. Time is relative. And we've all known this. It's just now that it's being, the idea of dark energy is being disproven or attempted to by this theory, the timescape model. And this makes more sense than dark energy. Now, dark energy does make sense because we have dark matter, we have matter and energy, but the only explanation we have that dark energy plays a role in is the expansion of the universe. And it doesn't matter in this context because we can't observe it objectively. How does the confluence of Lorentz transformations, the invariant speed of light, and the intricate interplay of space and curvature and general relativity exclude the paradoxical implications of time dilation within non-inertial reference frames, particularly in scenarios involving high velocity travel? It doesn't. It doesn't, has no confluence on that. Well, let me just double check. You're correct in this, yeah. So did time move faster or slower in the early universe? It would have moved. I suppose it depends. Because whether or not immediately post Big Bang, we had a lot of energy but no matter, so time moved very, very fast. But then this matter all became, so the matter came out of it. And the more matter that came out, that coalesced from this energy, the more gravity was produced. And then that became slower time. Hello from Canberra. We don't know how old the universe is. And when we're looking at something like this news article, enough water to fill trillions of Earth's oceans found in deep space, 12 billion light years away, circling a quasar, this is what I want to tie this to. Whether I don't like how the universe ends is not a question that I can answer. I'm not a physicist, nor am I a cosmologist. But thinking about relativity and our space in the universe, where we're looking can be much farther or much closer or much later in time than we think, much earlier in time. People saying that we are the center of the universe have egos the size of 10 times of Mount Everest, or they're just really like religious. It would have moved relatively to the object that you're talking about. Yeah. What's the most interesting question to you regarding this? Well, the most interesting question to me regarding this is, first of all, how old is the universe, actually? How old are we in the universe? How old is our galaxy? Beyond that, what is the time dilation difference in development of galaxies? Like, again, in these voids, including in ours, there are galaxies. There's not galactic clusters as much. And also, the dark matter is what's holding all of these together. That's the glue. Why, in the voids, are there still... How fast are the voids moving? How fast are we inside the void moving relatively to the rest of the universe? Because again, the universe is expanding. So how fast is this moving this way in comparison to this moving that way? And beyond that, if time moves faster in the Boots void than it does in the Canis Major void, And from our perspective, one of the answers to the Fermi paradox, other than the dark forest theory, being that the universe is quite young, and prior to the last couple, like maybe 2 billion years, there was a lot more chaos in the universe. It was much less stable. It was much less able to produce consistency in planets and galaxies that could produce life. How true is that we could be one of the earlier civilizations, which is why we haven't encountered aliens, because there hasn't been much time for other civilizations or even intergalactic powers to develop. I mean, again, us as well. But how different is that based on the time dilations in these voids? We think, again, the universe is 15 billion years old, but if it's 50 over there, then from the perspective of the Boots void, there would have been significant time for civilizations to develop. What if we're the first? Well, I mean, that is a theoretical answer to the Fermi paradox, based on our perspective of time and where the universe started, when the universe started, relatively. But that might all be gone. All of this might just disappear. And in functional, utility, I think we need to adopt this into, I mean, there's so much here, right? If you're looking for something 12 billion light years away, this quasar, which is actually well past this, but let's say you're looking over here. Let's say the quasar is right where my mouse is. We would have to account for different mass and different amounts of time dilation through the gravity wells of light traveling to where we're looking for. So if we say 15 billion years, we would have to math all of the space that it has to travel through to actually get an idea of how far this thing actually is. The age of the universe is different in different places. Send me a clip of this. I will. I took a clip of it. Space can expand faster than the exact speed of light, which doesn't violate Einstein. Well, yes. And none of this, all of this, by the way, is without even touching on quantum physics, which is well beyond my understanding, bar just the double slit experiment. Now, again, there are those out. There's the big crunch. There is the big rip. There is the idea that the universe will just collapse into a dense piece of matter and then explode back into another big bang. There are so many, but we can't wrap our head around that. That's fine. But what we can wrap our head around is looking out into the cosmos and understanding how far something actually is. And we've been, I've been saying this for a month now, because we've been covering some science stuff every now and again. 12 billion light years away is 12 billion years ago. That's not necessarily true. It matters in, we want to go to space, right? President Musk wants to colonize Mars and we want to go do interstellar shit. Okay, we need an understanding of this. And it is wild that it was never actually considered, because space is homogeneous enough that we don't need to add this in, is the dumbest fucking excuse. I think the current most accepted one is that matter will just continue to spread out until, that's heat death of the universe. And honestly, that's the one that I would subscribe to. And please, could you finally adopt metric? Look, I do metric in some things. I do imperial and other things. It's hard, all right? I do metric with, I don't know, speed and temperature. I have a lot of American viewers. I gotta translate for people. They don't know metric. So this, by the way, also, unrelated to the idea of time dilation, is also just really cool. I just wanted to bring up the time dilation because of this claim of it being 12 billion light years away. I mean, the space we can currently travel to is homogeneous enough, no? Yes. With the space we can travel to is homogeneous. However, if we're trying to, I don't know, build a understanding of where, how long has the universe existed, the acceleration, the expansion of the universe, then we would want to know these things. And that's what the Euclid telescope is trying to do as well. If you haven't seen. But also, just in the last couple months, we have been learning about how much more water there is in the greater universe than we thought. Neptune and Uranus have H2O on them, two most common gas planets in the universe, types of gas planets, meaning that there's probably quite a lot more of them. We're finding quasars with 140 trillion times all the water on Earth's oceans combined, just spilling out of it. Space is interesting, but also our understanding of it is, we're not there yet. We don't know anything about anything. We think we know shit, but every time we think, like, agree on a theory, it's just going to get disproven until we can actually go and make attempts to do experiments physically in these areas, which is why I actually really like Euclid. If you haven't seen Euclid, I'll post the link to it in the chat. This idea of mapping out space and time all the way back to the Big Bang and trying to understand the expansion will actually add relativity into it, because it's not being done, it's being observed. A lot of the moons on Jupiter, they think, have like oceans under the surface. I think if we find other life, like bacteria, it'll be there. Yeah, absolutely. Titan, I believe, is one. There's almost certainly bacterial life in underground oceans on Mars. We also found that out. Not even just frozen at the poles. There are undersea oceans. The water sank under the ground in parts of Mars that could hold bacteria. Also, that makes me think of the creepy Doctor Who episode, The Waters of Mars, and I don't want to do that. Europa is another one, yeah. Ganymede could theoretically have ice. Life isn't rare. Humans aren't unique. Yes, that's really where it comes down to. I don't think, like, first of all, you don't need water to have life. You can have silicon-based life forms. But for carbon-based life forms, so far we found we need water. And we thought for a long time that water was scarce. Remember, not even 5 years ago, if we would ever talk about, like, what if aliens ever invaded and why would they come here? The answer would be, well, they would want our resources. Water is scarce, right? That's not true. NASA has some missions to go there in the late 2020s. Well, NASA's getting their funding cut, like, immensely, so who knows? Speaking of time, though, we've now observed negative time in quantum experiments. This is well above me and my understanding, so bear with me here, but I just do want to get, like, some of this, at least in my brain and in your brain. Well, our current ideas work until 10 to minus 40 seconds after the Big Bang. Yeah, what the fuck is negative time now? If we just talked about time dilation and the speeds at which time are moving, but now we have something called negative time. Of course, quantum shit would have negative time, yeah. Well, so scientists have long known that light can sometimes appear to exit a material before entering it, an effect dismissed as an illusion caused by how waves are distorted by matter. Now, researchers at the University of Toronto, through innovative quantum experiments, say that they have demonstrated that negative time isn't just a theoretical idea, it exists in a tangible physical sense, deserving closer scrutiny. The findings yet to be published in a peer-reviewed journal, so again, take it with a grain of salt, have attracted both attention and skepticism, which skepticism is healthy. The researchers emphasize that the perplexing results highlight a peculiar quirk of quantum mechanics rather than a radical shift in our understanding of time. This is tough stuff even for us to talk about with other physicists. We get misunderstood all the time. While the term negative time might sound like the concept lifted from science fiction, defends its use, hoping it will spark deeper discussion. Years ago, okay. When light particles or photons pass through atoms, some are absorbed by atoms and later re-emitted. This interaction changes the atom, temporarily putting them in a higher energy or excited state before they return to normal. Yeah, okay. In research led by Daniela Angulo, the team set out to measure how long these atoms stayed in their excited state. That time turned out to be negative, meaning a duration less than 0. Okay, now my brain is broken. No, actually, they did say, to make it clear, there was no time travel involved. But this has broken my brain. They tried to measure how long the atoms stayed in their excited state, and it turned out to be less than 0. To visualize this concept, imagine cars entering a tunnel. Before the experiment, physicists recognized that while the average entry time for 1,000 cars might be, for example, noon, the first cars could exit sooner, say 11:59. This result was previously dismissed as meaningless. What Angulo and the colleagues demonstrated was akin to measuring carbon monoxide levels in the tunnel after the first few cars emerged, finding that the readings had a minus sign in front of them. The experiment conducted in a cluttered laboratory, blah, blah, blah. Okay, I kind of get it now. All right. So yeah, we don't want to say anything traveled back in time. That's a misinterpretation. The explanation lies in quantum mechanics, where particles like photons behave in fuzzy probabilistic ways rather than following strict rules. Right. So instead of adhering to a fixed timeline for absorption and re-emission, these interactions occur across a spectrum of possible durations, some of which defy everyday intuition. This is kind of meaningless. Yeah, this means nothing. Fuck that one.